Hi everyone, this is Mrs. Musoff. We're going to be starting our next section today, and that's going to be talking about continuous functions. Alright, so when we talk about continuity, we could be talking about it on a specific interval, or we could be talking about it overall as a function. Alright, so if we're talking about on an interval, we would say a function is continuous on an interval. Remember, IFF, that stands for if and only if. So a function is continuous on an interval if and only if it's continuous at every point on that interval. All right. In contrast, a continuous function is one that's continuous at every point in its domain. All right. And the easiest way to think about continuity is imagine drawing the graph. If you can graph it without lifting your pencil, that would mean it's continuous. All right. So if at any point if you're drawing the graph and you have to lift up your pencil to do something, that would be discontinuity. Okay, and then another side note is that all polynomials are continuous. So if you just have, a quadratic or a cubic or a quartic, anything like that, if it's a polynomial, it's automatically going to be continuous. Okay. Another part of continuity is continuity at a specific point. So like at a specific x value, if I said, is the function continuous at x equals 5, right? That would be continuity at a point. And there are two separate definitions for that depending on if you're dealing with an interior point, which in this picture would be like C, letter C, right? That point right there is an interior point because it's inside the interval. Or if you're dealing with an end point, and that'd be like A or B because those are the end points of this interval. Okay, so the two different, kind of slightly different definitions. If it's an interior point, a function, f of x, is continuous at an interior point C of its domain if the limit as x approaches C of the function is equal to f of C. All right, so if the two-sided limit is the same as the actual function value, that's how you know it's continuous. All right, and it's a very similar definition for endpoints. The only difference is at an endpoint there is no two-sided limit, there's only a one-sided limit. So a function f of x is continuous at a left or right endpoint if the limit as x approaches, let's start with the left endpoint, so as x approaches a from the right is equal to f of a. And same thing on the right side endpoint if the limit as x approaches b from the left is equal to f of b. So basically if these limits match up with the actual point, that's how you know it's continuous. All right, when we talk about discontinuity, there are 4 types of discontinuity, but 3 of them show up the most, and those are these 3 right here. Okay, we have a removable discontinuity, which is basically a hole, whether it's filled in somewhere else or not. Right? Either way, those would both be examples of holes. Okay, and therefore removable discontinuity. So from now on, when you see a hole, we also want you to mention like, oh, that means it's a removable discontinuity. Okay. A second type of discontinuity is a jump discontinuity, and that's most often seen with piecewise functions, where you're graphing one piece and then you jump in order to get to another piece. All right, that's a jump discontinuity. With jump discontinuities, the one-sided limits exist, but they are different. And so that means the two-sided limit would not exist. And then the other main type of discontinuity we see is infinite discontinuity. And that's basically when you have a vertical asymptote, because it means the graph is going on forever towards positive or negative infinity. All right, so here's an example of that. Okay, I'm going to flip the page over. The 4th type of discontinuity, let me scroll up here, is an oscillating discontinuity, which doesn't show up often, but just to see an idea of when it could. This is the function sine of 1 over x. All right, it's oscillating, and then it kind of just cuts out here. That's an oscillating discontinuity. All right, so in these examples, we find points of discontinuity. So find like the x values, right? It's not continuous at x equals blank, right? And then we determine what type of discontinuity it is. Is it removable, a jump, or an infinite? All right, so that's what all of these examples are showing. Like in letter A, y equals the cubed root of x plus 2. You've got a couple options for determining points of discontinuity. You could sketch the graph, which is what I show here, right? We know what the cubed root graph should look like. It's just shifted left 2, so I drew it here. All right, but even if you didn't sketch the graph, because we know the general idea of this graph, right, the parent function, we should know that cubed root functions are continuous at every point in its domain, which would be from negative infinity to positive infinity. So because it's continuous from negative infinity to positive infinity, we'd say there are no points of discontinuity. All right. So if you recognize the function and you know that that function, when you graph it, is continuous everywhere, use that to your advantage, okay? And don't feel like you have to draw the graph if you know that. For letter B, I saw this was a rational function. Anytime you have a rational function, your first thought should be, is there a hole, right? Which we now know is called a removable discontinuity. So I factored it, and I said, oh, look at that, there is a hole, right? X plus 1's cancel out. And so because there's a hole, that x value, -1, would be a removable discontinuity. So I'd say there's a removable discontinuity at x equals -1. And that means it's continuous everywhere else because I can see the function I'm left with is just linear. Right? So if I needed to know where it's continuous, I'd say it's continuous from negative infinity to -1. And then from -1 to infinity, it's just not continuous at x equals -1. Right? You'll see in your homework, sometimes we then ask you to give a formula for the extended function to make it continuous. If it's a removable discontinuity, to make it continuous, you literally just remove that discontinuity. Right? So we take the hole out, and the function that's left is the one that would be continuous at x equals -1. Okay? So it sounds like a complicated thing we're asking, but it's really just taking out the hole. Okay? You can really only do that with removable discontinuities because, like we said, they're removable, right? So you can take them away. All right, letter C and D, again, just more examples of similar concepts. In letter C, you know that graph has a vertical asymptote at x equals 2, so you don't have to graph it, but if it helps, feel free. Vertical asymptotes are infinite discontinuity, so I'd say that it has an infinite discontinuity at x equals 2. And part D, this should be a graph we're getting more and more familiar with. We've seen it on a lot of homework assignments. All right, x divided by the absolute value of x is this graph right here. And so because it jumps from -1 to +1 at x equals 0, we'd say there's a jump discontinuity at x equals 0. Okay. And over here you can see I just wrote some extra notes to help you understand why this function turns into this graph. So feel free to take a look, but as long as you know how to identify the graph, you should be able to find your discontinuities. Alright, so that's all for these notes. I'm going to go through a few extra examples in another video, so feel free to watch that if you think it'd be helpful. Thanks for tuning in.